Hello, class. Just kind of a disclaimer. This video is going to be a little longer. I try to keep them short. I used to keep them under 5 minutes, but this semester I seem to be going a little longer. I guess I'm more talkative this semester. But these are optional. You don't have to watch them. They are not necessarily part of the course content, other than the fact that I try to bring something that's going on right now in research or in society and bring it into the class material. And also try to lift you up as much as I can, because hey, who doesn't need a little boost in the right before the weekend, right? So this article is about nuclear chemistry, and so uh, a couple things are different about when we look at a nucleus. So, and this is where I'm gonna explain some of the background, because I don't know how far you've gotten in this class, and but just to remind you, if you've already learned this stuff, that's fine. So, atoms are made of smaller particles: protons, neutrons, and electrons. And electrons occupy most of the space of the atom, and they're generally speaking on the outside, and the nucleus is where most of the mass of the atom is, and they are typically found close to the center. And you can see I'm using the word typical because, due to uncertainty, we don't know exactly where position and momentum are of particles. So, and as far as we can tell, electrons are fundamental particles. We've never been able to break apart an electron. You can break apart protons and neutrons. So protons and neutrons are made of smaller particles called quarks. And another difference between protons and neutrons and electrons are that protons and neutrons engage what's called the strong force. So according to physics, there's four fundamental forces. So four forces: there's gravity, the weakest force; electromagnetic, sometimes called electrostatic, sometimes called electric. So electromagnetic force, nuclear weak, and nuclear strong. So now there's a new force that we don't understand: dark energy. So maybe there's five fundamental forces, but it turns out the nuclear weak force and electromagnetic force are the same force. The nuclear weak force is how quarks bind together to form other particles like protons and neutrons. But then there's the strong force, which is on its own, and the strong force is exhibited between various particles. Protons and neutrons have the strong force between them. There's other particles that have the strong force. Pions, for instance, have the strong force, but electrons do not. So electrons do not have the strong force. And if you think of the nucleus of an atom, the nucleus of the atom often, with the exception of hydrogen, there is a bunch of positively charged particles in very close proximity to each other. And the idea is, well, there needs to be a force that's stronger than the electrostatic repulsion, because you put a bunch of positive charge together, it wants to blow up. But then if you have the nuclear strong force, these positive protons actually have an attraction to each other. And that attraction is stronger than the repulsion between the electrostatic repulsion. And so that's what I call the strong force. I thought that we had pretty much figured a lot of this stuff out, but it turns out we have not. So some other things about protons and neutrons: just like electrons, they have wave functions. If you've studied the quantum mechanical model of the atom, the electrons occupy space. We call them orbitals. And similar to electrons, protons and neutrons also have orbitals. Unlike electrons, though, protons and neutrons, the energy spacing between them is so high that they essentially do not interact with each other. But like electrons, they fill into specific energy levels, and from that they have structure. You can learn more about that in the Pauli exclusion principle and the Aufbau principle in this class or other classes. So just like atoms, just like matter in general, matter has structure, right? Energy, on the other hand, they're made from bosons. Bosons do not follow the Pauli exclusion principle, therefore they do not have structure, at least not externally or macroscopically have structure. Whereas protons, neutrons, and electrons, electron clouds, and nuclei, they have structure. And there are consequences of that, and which is a good thing, though, that they have structure. Otherwise, we would not, because we're made of matter, we would not have structure. And another important thing to note about protons and neutrons is, and this works for electrons too, when you have two of them, an even number, they release what's called the pairing energy. Same with electrons, they have pairing energy, but it's much, much, much less than protons and neutrons. So when you see atoms, the stable atoms tend to be even numbers of things. So even number of protons, even number of neutrons. Generally speaking, the more even number there are, the more stable a nucleus is. And more stable also means it's lower energy, and it also means it's not radioactive. A radioactive nucleus is an unstable nucleus. Okay, so that's your brief overview on this. And about this article, though, this is just plain old fundamental research. This research that we're looking at right now is just looking at, we're trying to understand the way the world behaves. Okay, plain old trying to understand the way the world behaves and looking at matter, just the properties of matter. So right now there is no application for this. But it's where maybe there will be in the future as we study these more and more. But this is just plain old, pure research. And what they're doing is they're looking at various isotopes. So isotope is an element that has the same number of protons, but it's different number of neutrons. And we're looking at specifically oxygen-28. So similar to electrons. So there's a periodic table down here later on. So there are a very stable number of electrons. Those numbers are 2, 10, 18, 36, 54, 86, and 116. So these numbers, 118. I'm sorry, 118, and not 116. 116 is over here. 118, and these are the magic numbers. So protons and neutrons have relatively low energy states as well, states of numbers. I mean, those are the magic numbers, and they are found, where are they found? Not down there. I saw this before. Here we go. 2, 8, 20, 28, 50, 82, 126. And so generally speaking, if there's number of protons or neutrons, these are particularly stable elements. And personally speaking, something that always kind of struck me as odd. So I always think about the king. The most stable element, speaking nuclear-wise, is iron. Iron, 26 protons and 28 neutrons. That is the most stable element. I always wondered why it wasn't nickel, because that would be double magic, right? Because double magic, and this is actually something that's been bugging me as myself as a scientist. That why is iron the most stable element and not nickel? And iron is important for stars because nuclear fusion. So when you bring elements together, or you fuse them together to form new elements, building up to iron, generally speaking, the process is exothermic, so it releases energy. And after iron, nuclear fusion is endothermic. It absorbs energy. So for classic stars, when iron forms in the core of the star and iron starts fusing, it's endothermic, and stars are made of gas, plasma, I don't know they're going to follow the same gas laws, right? So like Boyle's law and Charles' law, same idea. But when iron fuses, energy goes down, and that causes the stellar core to contract. And if it contracts enough, it will implode, and that causes a shock wave shooting out, and that's a type 2A supernova. The star will explode. So, and the reason for that is because of the fact that iron is the most stable element. So right now, right away, there's something wrong with our understanding, right? So why is iron so stable? And when I read this article, I'm like, oh, this is cool. Like maybe this is explaining more and more. And so think of these magic numbers, and we're finding some things that are just odd. So for instance here, beryllium 10. So beryllium is a halonucleus. So beryllium has 4 protons, so they here denoted in red, 4 protons, and then 6 neutrons. And it's almost like there's 2 helium nuclei and then 2 neutrons, and they say that it orbits. And it's there. The neutrons kind of exist in this certain wave function here. It's almost like 2 nuclei and then a third sort of like area of nitrogen density. So we're not really seeing this. I mean, this is not something that we're observing by actually finding the location. Unless they're doing it some sort of trick with collisions, I think that this is from calculation. So just so you know where they're getting these from, this is based off of the theory of quantum mechanics. And also, if you read later in the article, some of these elements, so where do some of the elements come from in this periodic table? You can form just exploding massive stars up to, well, rubidium, maybe as high as zirconium. But many of these elements are formed by colliding neutron stars. And this is not an astronomy class, although I love astronomy. That just a very, very neutron-rich environment forms these other elements. And maybe also some low-mass dying stars can form it. But it looks like the majority of these elements, like some of my favorite, platinum and gold, right? I love those elements. Those are formed by predominantly colliding neutron stars. So that also tells us how old we are as a solar system. That it's about a little under 14 billion years since the Big Bang expansion event, and how much how much time has gone on in the cosmos. One of them including collisions of neutron stars. So amazing. But one of the reports in the so those would be formed by a bunch of neutrons coming together in the lab. We form them this way. So they're specifically trying to find oxygen and oxygen 28. So oxygen has 8 protons, and oxygen with 20 neutrons would seem to be very stable. So they're looking for these exotic sort of nuclides or isotopes that have different number of neutrons. And surprisingly, they found out that oxygen 24 is stable, but oxygen 28 is not. Based off of our current understanding, oxygen 28 should be stable. So that's weird. That's weird. And it's not weird. It's chemistry is an observational science, and we're observing this, but it doesn't fit with our explanation. Or what we thought. And this is one of the things I also want to impress upon you. Science is tentative. So science is not we're done. We've figured everything out. There's nothing else to explore. There's nothing else to understand. We're done. No. We'll probably never be there. That would be unfortunate if we ever did get there, that we understood everything, because, I like learning, right? There's nothing left to learn. I mean, then maybe that's when the universe ends. I don't know, right? So when learning stops. Good philosophy for a teacher, right? So we're always learning new things, and we thought that oxygen 28 would be stable, but it turns out that oxygen 24 is stable. Well, that's weird. Right? So why is it stable? Why is oxygen 28 unstable, and why is oxygen 24 more stable? So we don't know. We don't know, and we're trying to figure it out. And it seems that one of our lack of understandings is in the nuclear strong force. So there's something going on that we don't quite understand. And like I mentioned before, with these, that where these elements are formed, and the strong, the most stable element is iron 26 or 26, 28 protons. So iron 56. Iron 56 is the most stable nuclide in the periodic table that we, or I should say that we know of now. Maybe now everything, who knows? Maybe there's a more stable one, but that's the most stable one here. I have many astronomy friends, and an astronomer says the periodic table is hydrogen, helium, and the rest are metals. So oxygen is a metal to a astronomer. And my counterpoint always was like, if I were you, I would organize a periodic table as lighter than iron and heavier than iron if you're doing nuclear stuff. But I don't know. They always look at me like I'm crazy. But well, that's kind of a true statement, regardless, right? But let me tell you one of my dirty secrets. I really love the show Ancient Aliens. So it's on the History Channel, and you have this guy with this big afro that is excitedly explaining things, and I think it's hilarious. But the reason why I think it's hilarious is because it's so bad. Like the science in it is so weak and terrible, and the terminology they use is like some ancient alien theorist believe, and like that's the whole thing with the scientific method. A theory is a proven fact. Although the ancient aliens is at best a hypothesis. It's not a theory, at least certainly not in the scientific ways. It's not, I would wager even to call it a hypothesis, because a hypothesis is an educated guess. So that's may not be that's not really, I don't know. Anyways, that's an argument for a different day. But if you follow the show, one of the secrets of alien technology is apparently elements 115. And that kind of always made me laugh. Element 115, it's first of all odd number of protons, so it's less stable, right? And it's less stable than even number of protons. And I really don't think, like, I mean, when it comes to the magic numbers and stability, I mean, there are rules changing. We see that in chemistry. We see this especially with electrons and the transition metals. There's numbers more than 8. So 8 is the octet rule that's often used in bonding. There are other numbers that are particularly stable or quasi-stable. But the odd number, element 115, the odd number doesn't have the pairing energy. And that's really a fundamental thing, right? So the pairing energy is something that is released and makes nuclei very stable. And there's quite a bit of energy released in that. And that's also the principle behind our nuclear weapons, is the odd number of neutrons. Uranium-235 and plutonium-239, those odd number of neutrons. And when uranium-235 or plutonium-239 absorb a neutron, it releases the pairing energy, and that's what causes the nucleus to excite and then break apart. And then the neutrons fly off, and then those repeat the process. So that release of pairing energy is the reason why our nuclear weapons work and how we can also get nuclear power. So that even number of nucleons is a very, very important thing. And so the element 115, I just like, nope, you're picking the wrong element there for your show. But I don't know, maybe with this it's different, but I'm pretty sure it's not, because for that reason. But I do love that show, though. It's I watched all the episodes, or at least like the earlier seasons. As it went on and further, it became kind of repetitive. So, but I've told students about that. They're like, I like that show too. So, I should get the afro. I don't have enough hair. I can't grow the afro like that guy. So yeah, this is a. I'm sorry, I said it's a long video, and I apologize for that. But I thought there needed to be a little bit more of a discussion on this, and and it's also kind of like we don't know what's going on. This is what we see, and uh, some of the takeaways from this is so we're still doing research. We're still trying to figure out how the world works. We haven't figured out how the world works completely yet, and things that we thought that we figured out, turns out we didn't figure them out. So because of that, we need to change the theory. The theory is wrong. So there's something wrong with these magic numbers. The magic numbers being the observation that these magic numbers seem to have a huge amount of stability. Stability means low energy. Stability means it sticks around longer. So that's another takeaway from that. Other takeaway from this is how the scientific method works. So now that we observe something that contradicts the theory is wrong. The theory is tentative. So now that we know the theory is wrong, we need to change the theory. So this is different than Platonic philosophy. So Platonic philosophy, where it's like there's a form of something and we relate it to the form, and right. So that's kind of the abbreviated version of Platonic philosophy. So scientific philosophy is more data driven and observational experiment. So now that we observe something, we're not comparing it to the Platonic form in a heaven. We are here on Earth or in the cosmos, and we're observing this, and what our observations are real, unless we're mistaken with our observations, right? But that's a different story. Observations and data are real. So speaking of real things, we humans are real, and we are wonderful things, but we also require certain things like food, like shelter, and ever increasingly humans are having mental health issues. So if you fellow humans are experiencing any of these issues, please feel free to reach out to me. Any academic issues. When I say academic issues, I mean, of course, with my class. I mean, that I'm the subject area expert, right? So it's my job to instruct you on this. So that's obvious. But I mean, if you need help maneuvering through the university, I can help you with that as well. So if you have academic questions that you wanna ask me, like not necessarily pertaining to the subject of this class. So, and I hope this finds you well. And I'm gonna shut up because I've talked too long. So you're like, hey, these online classes, why is the professor keep on yapping? So I will say aloha for now, and again, apologies for the long message. So have a nice weekend. Goodbye.